the limit of 1 over x when x approaches 0 is equals to 1 over 0, which is infinity. The limit of 1 over x squared when x approaches 0 is equals to 1 over 0 squared, which is 1 over 0, and is still equals to infinity. So, two of them are the same. Right? Wrong! Limit is not as simple as you think. Hey guys, welcome to Emaths. Today we are going to compare the limit of 1 over x when x approaches 0 and the limit of 1 over x squared when x approaches 0. We have to first understand the concept of limit. Let's say, for example, we have a very simple function f of x equals to x, and we want to find the limit of f of x when x approaches 0. In your textbook, they will show you a table of values of x and f of x. And because we want x to approach 0, so maybe we start from 0.1, then closer to 0 is 0.01, then 0.001, 0.0001, until we reach 0. What we are doing here is that, for example, let's say we have a graph of function, okay, f of x against x. 0 is here. We start from 0.1, then go closer and closer to 0, and see what happens when x equals to 0. Okay, then we will find the value of fx. When x equals to 0.1, f of x will just be x, which is 0.1. When x is 0.01, f of x is 0.01. Similarly, that will be the same for all of them. Okay, 0.0001, and as you can see, the number gets smaller and smaller and smaller, and eventually you will reach 0. So from here, we will write the limit of f of x when x approaches 0 is equals to 0. But that is not enough, because we only do from the right. So we have to put a plus sign here, and this is called a one-sided limit. Then you might ask, can we do it from the left? Yes. Okay, let's say we have a negative 0.1 here, and we do it from the left. We just put negative sign for all the value of x, and for f of x, same thing, we'll put a negative sign in front. As you can see, the number get bigger and bigger and bigger, and it will become 0 at the end. So we'll write limit of f of x when x approaches 0. From the left, we put a negative sign, is equals to 0. As you can see, both of them are the same. So maybe I write here, the limit of f of x when x approaches 0 from the left is equals to the limit of f of x when x approaches 0 from the right. What can we say about this? Well, since they are the same, we will say that the limit of f of x when x approaches 0 from both sides exists. Or maybe we say that it is defined. And what is the limit? Is 0. In the example from earlier, this is how we define a limit. If f of x becomes arbitrarily close to a single number L, means it's very close to L until we cannot tell the difference by looking at it. As x approaches c from both sides, then the limit of f of x when x approaches c is equals to L. However, this definition is not good because it's very technical. Number one, we don't know the meaning of f of x becomes arbitrarily close to L. And number two, we don't know the meaning of x approaches c. So we need to come up with something else to have a better definition for limit. Now we have a look on epsilon-delta definition of a limit. Epsilon and delta are both very small positive numbers. But even though they are very, very small, epsilon and delta are still greater than 0. Okay? Now look at this graph of function. We have a point here, CL. And because epsilon and delta are very small numbers, so actually we enlarge this graph a lot already. Okay? As you can see, L is in between L minus epsilon and L plus epsilon. So when we write in inequality sign, we will write L is greater than L minus epsilon, but is smaller than L plus epsilon. And we know that all the points on this axis are called f of x. It can be here, it can be here, it can be here, it can be here, it can be here. And this is the f of x that we want. So any point from in this range, which is the f of x, and the distance with L, then we put a modular sign because it can be positive or negative, is smaller than epsilon. Okay? Similarly, all the values of x that we want will be within this range. And c is in between c minus delta and c plus delta. So the x here minus c will be smaller than delta. Okay? Simple, right? With these two inequality, we can give the meaning for f becomes arbitrarily close to L and x approaches c. From here, we can establish a formal definition for limits. When we let f of x be a function defined on an open interval containing c, like in this interval we have a c inside, except possibly at c itself, meaning when x equals to c, fx is undefined, and L is a real number, means this is a real axis. The statement limit of f of x when x approaches c from both sides equals to L would means we'll take these two inequality. If the distance of any x point and this c is smaller than this small positive number delta, and remember it is greater than 0, then the distance of any fx point and this L is smaller than epsilon but is greater than 0. So this is a formal definition of a limit. Okay? Take note, yeah? When the limit exists, it means it will be unique. We cannot have two limits at the same point. Okay? Finally, we'll get into our topic today. But I will start from this part first. Consider a function f of x equals to 1 over x squared, and we want to find the limit of f of x when x approaches 0 from both sides. Same thing, we have a table of values when we approach 0 from both sides. Notice that we have an x squared here. So when we square the negative x, the value of f of x will be positive. So the limit of f of x when x approaches 0 from the left is equals to, the number get bigger and bigger and bigger, huh? So eventually we'll have positive infinity. Then how about this part? Okay, obviously the number also get bigger and bigger, so the limit of f of x when x approaches 0 from the right, we put positive, equals to positive infinity. As you can see, two of them are the same. So this limit is unique and it exists. So the limit of f of x when x approaches 0 from both sides is equal to positive infinity. Then you might ask, why do we have to take the limit from both sides? Can we just right away submit the value of x to get our limit? The answer is no, because sometimes the limit from the left is not the same as limit from the right. And I will show you in the next example. Sometimes we'll have limits that fail to exist. For example, this function. Same thing, we'll tabulate a table of values. When x is positive, we'll have a very nice 10, 100, 1000, and so on and so forth. So the limit of f of x when x approaches 0 from the right is equals to a positive infinity. No problem. However, because we didn't square the value of x below, so when x is negative, we'll have negative f of x, which is a negative 10, negative 100, negative 1000. For this part here, the limit of f of x when x approaches 0 from the left is equals to smaller and smaller, huh? Negative infinity. Two of them are not the same, so they are not unique. Therefore, the limit does not exist. We will write the limit of f of x when x approaches 0 from both sides is undefined. Because we don't know it's positive or negative, therefore undefined. Okay, I know you might still say it doesn't make sense because both of them are 1 divided by 0. How can they be different? Well, when you look at their graph of function, this is a graph of 1 over x, which is a reciprocal graph. When x equals to 0, it diverges. 1 to positive infinity and 1 to negative infinity. Two of them are not the same. It is not unique, so it doesn't exist. Therefore, the limit of it we cannot define. It's undefined. However, when we have a graph of 1 over x squared, as I said earlier, because we square the value of x, so it will be positive from both sides. We will have a same limit when x equals to 0 from both sides, which is positive infinity. So it is defined, and we can write it as positive infinity. In fact, when we have a function of 1 over x to the n, when n is odd, we will get the same result as this part. When n is even, we will get the same result as this part. Okay, this is the last thing I can do to convince you. When we type in limit of 1 over x as x approaches 0 in Wolfram alpha, we will get two-sided limit does not exist. But when we type in the limit of 1 over x squared as x approaches 0, we will get positive infinity. Okay, then what about symbol lab? Some students like to use it like me. Okay, we'll have the limit of 1 over x when x approaches 0 equals to diverges, like what I explained just now. Okay, positive infinity and negative infinity. Then when we square it, we'll have, positive infinity. Are you convinced now? Moral of the story: two of them are not the same. That's all for today. If you like Emacs, see you guys in the next video.